Good morning, everyone. In this class, I will solve with you 6 examples or a problem, and I hope these examples will help you to understand this chapter, right? Chapter 4. Okay. First example on Bernoulli equation. It's a direct application on Bernoulli equation. We have water bottle here. The height of this water bottle is 1.5 feet or foot, and we have a cup to be filled, and it's seated beneath the table of 2 meter, 2 feet or 2 foot height, right? So what we're gonna do, we need to calculate how much time, the time needed to fill this cup in 2 cases. First case, when this bottle is almost filled with water. The second case, when the bottle is almost empty. So what we're gonna do, guys, here, it's very direct application. We're gonna assume 2 cases, case 1 and case 2. So for the first case, delta Z will be 1.5 plus 2 foot, right, or feet. So the 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 rate of flow will be higher than when it's empty, because delta Z only will be 2 in the second case. Let's see how we're gonna solve this example together. You see, guys, we just direct apply the Bernoulli equation. As I told you, in this case we have so if we look at the figure here, you will see that P is atmospheric pressure in the both cases. So P1 is gonna equal P2, right? Nice. V1 will be almost zero. There is no velocity. As I told you, when we have a flow, when the water is flowing out from big water body through a small pipe or a nose or a hose, whatever. So we can say the water velocity at the water body is gonna be zero. So, and we're gonna assume Z to be zero at the lower level here, you see. So very simple here, Z gonna equal V square, V2 square over 2G. So we can calculate V. So this is how we're gonna solve this equation. So we have 2 cases. So the first case, velocity will be 15 feet over second. So because we need, how we gonna calculate the time, we need to know the flow, and the time is gonna equal the volume of this cup over the flow. So what is the flow here in this case, guys? We have velocity, we have area. We know that the flow is gonna equal area times velocity. So I can get it here. So time for the first case is gonna be 1.6 second. In the second case, the only difference here is this 3.5 become 2, because the water will be in this side here. It's almost empty. So we can get the time which must be bigger than the first case. Right? This is very important. So that's how we can deal with such examples. So the answer is 2.2. I think it's very straightforward. Right. The second example also in Bernoulli equation, but now we have something called pressurized tank. So this is a pressurized tanks, doesn't mean that we must use energy equation, because this is just like a pressure. We don't have pump, you see. So we have a pressure here, because why we get pressure? Because we have a closed tank. So this cover here will separate the water inside the tank from the atmosphere, so we can't consider this pressure as atmospheric pressure. So now we can't delete, or we can't assume that P1 is gonna equal P2 atmospheric pressure. No, at all, we can't do that. So what we're gonna do, look at the answer here. We will have case 1 and 2, so we're gonna keep P1, which is equal 250 kilopascal. We're gonna keep P2 here, which is like atmospheric pressure, guys. But same as we did before, this V here is gonna be 0, and we have velocity here, so that's fine. So we can calculate the volumetric flow rate very easily. So we did this equation here, we remove Z2 only. So only Z2, just as you not remove, it's equal 0. Other parameters is still there, and V1 is 0. So we get this equation, just direct substitution, we're gonna get the velocity. Velocity is 18.7 meter over second. Nice, I have velocity, I have diameter here. Very easily I can calculate the volumetric flow rate, or flow rate, which is equal 0.147 meters cube per second. This is the only difference here from the example that we did in the slide, in the notes, is we have extra pressure. Right, we have extra pressure. So we must be careful about all these terms. We need to know the atmospheric pressure here, we need to know this value, etc. Right? Interesting. I hope you understand the answer. Not difficult at all. Yes, we have also a nice example here, guys. Direct application also of Bernoulli equation. You see, guys, here we have a fire hose with velocity of 1 meter per second. And we got a pressure 200 kilopascal. So, but this pressure inside comes from the machine, the fire machine. At the exit, here at the exit, we know that the pressure will drop to be atmospheric pressure, 101 kilopascal, right? And we need to assume that there is no change in the height, this is level, it's horizontal. So we need to use Bernoulli equation to calculate the velocity of water exit at the nozzle here, right? So density, gravity, all these issues. So we apply Bernoulli equation. We know that Z H with H, gun with gun. You see, we still have velocity here. We still have velocity at the nozzle and velocity at the fire water tank, right? So we're gonna keep V1 and V2. Only we just remove it Z or H here in it. So we have this equation. Straightforward. I have all parameters. I have rho, I have V1, I have B1, and I have B2. So I only need to calculate V2, which is 14 meter per second over second or per second. Right. Very simple and very direct. So the concept here, guys, you need to understand the scenario. Read the question twice. So if we have, as example, the nose level is higher than the tank with like 1 meter, so we're gonna use here, we're gonna keep H2 to be like -1 and etc. So we need to be careful about all giving information. Okay. Another example here, problem number 4. Also Bernoulli equation. We have here, guys, a fuel refinery, ethanol, etc., whatever. We have a flowing in the pipe of velocity 1 meter per second. The pressure, atmospheric pressure, 100 kilopascal. So here we need to know how much needs the ethanol to be at pressure of 2 atmospheric pressure. So we need to know, we need to pressurize this ethanol to be under pressure of 2 atmospheric pressure on the lower level, right? So we need to know how far much the pipe drop in height in order to achieve this pressure. So I need to know how much I must drop in the elevation to maintain this pressure. Assume velocity doesn't change. We can assume that V1 is gonna equal V2, and density of ethanol is 789 kilogram over meter cube, and the gravity, etc. All this. So we have this equation here. We assume V1 is gonna equal V2, V1 equal V2 done. So you see here we keep P1, B2, and rho GH and rho G. You see this is like a different figure of the equation. You can use the regular figure. It's fine. So all what you need to know now we need to know delta H. How is the difference between the two levels? So very simple, very straightforward. You need to be careful about the numbers, about the units. So we need like a drop of 13.1 meter to maintain or to keep this pressure at the bottom side, right? Problem number 5 here, general energy equation. You see guys, we have water pipe and we have two diameters for this water pipe. The first one 15 centimeter, the second one is 8 centimeter, and there is a reducer between these two pipes. Pressure here is 480 kilopascal. Pressure at the right side 445 kilopascal. So this is the information, and we have flow rate 0.035 meter cube per second, and the pipe is horizontal, so Z1 is gonna equal Z2 finish. So what we need to know, guys, okay, determine the irreversible head losses or head losses in the reducer. We need to know head losses, which is HL, right? Okay, so I have this equation, general energy equation. I write it. So I look, we have pump, there is no pump. Z1 equals Z2. We have turbine, no turbine. So we're gonna remove turbine, Z2 and Z1, etc. Yeah, we must keep P1, V1, P2, V2, and HL. Why? Because it's not same velocity here, because different diameter. So velocity gonna be changed. So this is the equation will be like that, will be in this way, right? So first step here, we need to know velocity. So I know the flow rate, so I calculate V1, V2, number one, finish, done. Then now I know V1, I know V2, I know B1, B2, finish. So HL is gonna equal 1.1 meter. So in this pipe, head loss is gonna equal 1.1 meter. So how much energy needed to maintain the flow, to maintain semi-flow within this head losses? So because we have head losses now, we need extra pump, we need extra energy to maintain the flow as it. Otherwise, we're gonna have like a drop in the flow. So very simple. We use this direct equation. The energy is gonna equal the mass flow rate. Sorry, we gonna use this equation rho Vg times HL. You're gonna use this equation. It's mainly the mass flow rate times G times L. So how we can, so this is rho times V times G times HL. 1000 flow, gravity, head losses. You're gonna get the value 406 watt. So it's about 0.4 kilowatt. Right? Yeah, this is very important. Example, I need you to understand it. Very simple, very straightforward. Right. And here is the last example. Yeah, this is very simple, very typical, like the last example in the slide. I don't remember the example number, but if you go back to the slide, you will find this very simple example. All what you need to know, you need to calculate the flow rate. We have pump. This pump is 15 HP, which is like horsepower. You will see how we can deal with this kind of unit. And we need to pump the water for up to 45 meter. Okay, and the efficiency of the pump 82%. Determine the maximum volume flow rate. You need to know how much what is the maximum flow rate. We have this equation for the pump. We have W pump here. GZ. This is same equation as I did before here in the previous example. So now the first step to convert to get the net energy that we can get from the pump, efficiency point 82 times 15, so it's 12.3 horsepower. So that's what we need to get now. So we divide all this over rho GZ 1000 9.8145. This conversion to convert 1 horsepower for what? So we must know, this is not required from you to remember, to remind guys. I'm gonna give you the conversion if it's needed. So each one HP will equal 745.7 watt. So we do the all conversion. So we see that we have the maximum flow is equal 0.0208 meter cube per second, meaning about 20 liter per second. Right? Very simple, very straightforward. That's all from me now, and I hope all of you enjoy this class. Okay, guys, see you later. Good luck.